This is the third lesson on the unit and transition metals. In this lesson, we're going to learn about transition metal complex ions, definitions of ligands and coordination numbers, and what the different types of ligands are. To begin with, we're going to go over some commonly asked exam definitions. Transition elements often form complex ions. These ions consist of a central transition element ion surrounded by ligands. A ligand is a species that forms a dative covalent bond with the transition element ion. Remember that a dative covalent bond is where both electrons are donated by the same atom. Another definition you need to know is that of coordination number. This is the total number of coordinate bonds formed between the central metal ion and its ligands. So in transition metal complexes, the ligand donates a pair of electrons. This can be represented by an arrow showing the covalent bond. In the example on the slide, the central transition metal is copper 2+ ion. 4 ammonia molecules are acting as ligands, and each one donates a pair of electrons to form dative covalent bonds with the copper ion. When dealing with transition element ions forming dative covalent bonds, we call the bonds coordinate bonds rather than dative covalent bonds. So in this example, there are 4 coordinate bonds, or a coordination number of 4. The ammonia is able to act as a ligand as it has a lone pair of electrons on the nitrogen. The formula of this complex ion is written as follows. The square brackets group together all the species in the ion. The ligand may be put in round brackets to show that the ligand molecule stays together. In this case, the NH3. There's actually an error I've just spotted on the slide, and it should be 2 round brackets around the NH3. The overall charge of the complex ion is shown outside the brackets, and this is 2 + 2. We will come back to the charges on complex ions shortly. So to recap the definitions, a complex ion is a transition metal which is bonded to one or more ligands by coordinate bonds. A ligand is a molecule or ion that can donate a pair of electrons to form a coordinate bond. In the example we saw, the NH3 molecule was acting as the ligand. The coordination number is the total number of coordinate bonds formed between the central metal ion and its ligand. You are most likely to be asked for an explanation of the term ligand. There are several different types of ligands that you need to know about, and these depend on how many electron pairs they donate to form coordinate bonds. The names of the 3 types of ligands are monodentate, bidentate, and multidentate. Monodentate ligand, as you can probably work out from the name, donates 1 pair of electrons and forms 1 coordinate bond with the transition element ion. Examples include H2O, where the oxygen has a lone pair and so can donate the electrons, NH3, where the nitrogen atom has a lone pair and can donate the electrons, and a chloride ion. Bidentate ligands donate 2 pairs of electrons and form 2 coordinate bonds with the transition element ion. They kind of loop round. An example is ethane 1,2-diamine, which has the formula NH2, CH2, CH2, NH2. This is often shortened to EN. The 2 nitrogen atoms donate the electrons. A further common bidentate ligand is C2O42-, where each negatively charged oxygen donates a pair of electrons to form a coordinate bond. Finally, multidentate ligands donate more than 2 pairs of ligands to form coordinate bonds. For example, EDTA4- has 6 pairs of electrons. Each nitrogen bonded to the central carbons donates a pair of electrons, and then the 4 oxygens with a negative charge each form coordinate bonds. This is all with the same central transition metal ion. The ligand bends round the central ion. You will often be shown an unfamiliar ligand and asked to suggest what type of ligand it is or to draw it bonding with the central metal ion. You need to consider the number of atoms with negative charges and or lone pairs. Look for oxygens and nitrogens. These come up really frequently. Moving on to the shape of these complex ions. The only one on the syllabus that specifically requires you to know and draw is the octahedral shape. That is formed when a complex ion has a central transition metal ion with a coordination number of 6 with monodentate ligands. The example shown on the slide is the copper-2 hexaaqua ion, which has the formula CuH2O6, so a central metal ion of Cu with 6 H2O monodentate ligands surrounding it. All the bond angles are 90 degrees. If you're asked to draw this in an exam question, this slide is exactly how it needs to be drawn. 2 vertical bonds above and below the copper, 2 wedged bonds coming out of the paper towards us, and 2 dashed bonds going back into the paper. Note that this is drawn with the oxygen forming the coordinate bond with the central copper ion, not the hydrogens of the water molecule. Any molecule with a coordination number of 6 will have this shape. Although you're only specifically asked about the octahedral shape, I think it's worthwhile mentioning other possible shapes that often come up, as you need to be able to apply your knowledge to unfamiliar examples. If the complex ion has a coordination number of 4, again with monodentate ligands, then it will almost certainly have a tetrahedral shape. There's one exception to this, which we'll cover in a minute. With the one shown on the slide, the tetrahedral shape, there is only one vertical bond above the central metal ion. 2 dash bonds go backwards and one wedge bond comes out the plane of the paper. The bond angle in a tetrahedral shape, if you remember from AS, is 109.5 degrees. The reason why you get 4 chlorides around the central metal ion rather than 6 is simply because the chloride ion is too big. The exception I was talking about before is cisplatin. Again, this cisplatin is specifically mentioned on the syllabus. You need to know what it is, you need to be able to draw it, and you need to explain what it does, what it's used for. It's a specific example of a complex ion that has a coordination number of 4. It consists of 2 ammonia molecules and 2 chloride ions around a central platinum ion. It is an anti-cancer drug and works by binding to DNA in cancer cells and preventing it from replicating. The complex ion itself has no overall charge because the 2- on the chloride ions cancel out the +2 on the platinum. Cisplatin is unusual in that it is not tetrahedral. Instead, it has a square planar shape, as shown in the diagram. All bonds are drawn with lines that are not dashed or wedged because they are all in the same plane. And finally, for today's lesson, we're going to look at either working out the overall charge on the complex ion, or more commonly in exam questions, working out the oxidation state or charge on the transition metal ion. This is really straightforward. Both these questions are approached in a similar way. You need to be familiar with or be able to work out the charges on common ligands. For example, you really should know that water and ammonia are both neutral and chloride is -1. You also need to look at either the charge on the overall complex ion or the charge on the transition metal ion. It's probably best if we work through this with a couple of examples. The copper hexaaqua ion has 6 water ligands and an overall charge of +2. As water molecules are neutral, the charge or oxidation state on the copper ion must be the same as the overall charge on the ion, which is +2. If we look at cisplatin, there are 2 neutral ammonia ligands and 2 chloride ions with a charge of -1, and so -2 altogether. The complex ion has no overall charge, so the charge on the platinum must balance out the charge on the chloride ion, so the oxidation state of platinum is +2. Now you have a go. Pause the video and try the question on the slide. The answer will be on the following slide. The answer is +3. As water is neutral, 2 chlorides have a charge of -2 and the overall charge on the complex ion is +1. Therefore, chromium needs to have an oxidation state of +3. We've covered a lot in this lesson, so I really recommend you go back over it and watch the video again. During class, we'll do lots of examples with lots of questions to help your understanding. See you next time.